Okay, so we were now, when we left the last time, in the middle of our, what in the lecture notes is application 8.1, and which I call calculating the photosphere of the universe. That is calculating where it lies when it occurred. But actually, we spent most of the time on Wednesday when we did this. We had to set this up by considering the era of recombination. We sort of accumulated in something which would, if we did the full plot, give us something like this. Here is the ionization fraction x, as we defined, of hydrogen as a function of temperature, temperature being there, and we got something which was something like this, where x equals to 1 is fully ionized, x equals to 0 was fully neutral hydrogen in our hydrogen universe. We discussed also why this was a good approximation, actually, for all our purposes here. This now occurred at about 3,500 Kelvin when we started to ionize the universe, or vice versa, the universe started to recombine if we start from the Big Bang and then walk toward lower and lower temperatures. Some key points were that it happened fast, so that when you look in cosmic time, this is a very small region, right? We learned how we connect the redshift to the temperature through T equals to T0, 1, plus the redshift. We also talked about why redshift is a convenient parameter for us, because if we want to convert from redshift to, say, time after the Big Bang, we need to insert a cosmological model upon this to calculate that. And then those type of assumptions come into play as well, which is why this is often a convenient time replacement coordinate for us. Now, you can see that this actually already, we said that like 2,500, the ionization fraction was down at side 10 to the minus 5 in our equilibrium analysis. And already here at like, say, 5,000, we knew that then it was fully ionized. It was at unity. So you can just see that this happened over a relatively short period in time when we consider the cosmic time. We also hinted toward why this indeed is where the background, the leftover Big Bang radiation, the cosmic background radiation, was released. Yeah, and that has to do with the main opacity source of the universe in this phase, I should say, which comes from Thomson scattering, electron scattering, that is scattering of free electrons, such as we have studied before in the course, okay? Now, of course, that requires you to have free electrons around. That is, if you solve the optical depth integral, you can do it in this form, kappa electron. This is the mass absorption coefficient, the mass density times the L. You can also write it as your Thomson cross-section times your number density of electrons, integrate over the path lengths. This we have calculated is a constant, 6.65 times 10 to the minus 25 centimeters squared. The number density of electrons, since we have a hydrogen universe, well, if the hydrogen is neutral, then there are no free electrons around to scatter against. So this opacity would just drop like a rock. Vice versa, if the universe is fully ionized, well, then we have our number of electrons, free electrons, okay? So that is how we tentatively assigned this period to this now. So now we want to show that we can indeed do these associations. And we will do this in two parts. We will calculate the optical depths, but we will start by considering another key concept that we have been discussing quite a lot, and that is the mean free path of the photons, okay? So the mean free path of the photons we know is 1 over the extinction coefficient, inverse units centimeters. Put in this, it's 1 over kappa, where we assume that we only have the Thomson scattering, which I will write as kappa E as kappa electron scattering, times the mass density. Now, for a hydrogen gas, like our hydrogen universe, you have already calculated an expression for this in your exercises. That was when you analyzed getting to the Eddington limit as an upper mass limit of a tentative upper mass limit of stars. Okay? Then you got it out to be 0.4 times the ionization fraction of hydrogen. And you can go back to your notes on that if you do not remember. Okay? Where 0.4, this is now in CGS units, okay? So centimeters squared per grams. And then, in our case here, this will, of course, be a function of the redshift, or the temperature. We can just use that to convert them. Then the density, we did the last time as well. We know that this is the present density, so rho 0, we called it. And then the density also increases as the redshift to the third powers. And we had this value as 3.7 times 10 to the minus 31 grams per cubic centimeters. That was our present day baryonic mass density. And we go back to class on Wednesday if we have forgotten all about what I'm talking about now, right? So what you can see is that you can write this as function, of course, of x of c, but also there, I did the numerical factor somewhere here, to 1.9 times 10 to the 21 centimeters divided by the ionization fraction of hydrogen. That's the mean free path of a photon in this era of the universe. So the question is, okay, but what do we compare this to, right? I mean, in the sun, we got that the average mean free path of a photon was like 1 centimeter, you know, and we used that to do some interesting analysis there. But we know roughly the scale of the sun, right? We can relate the centimeter there. Here, this is not so trivial. What do we relate this mean free path of a photon in the universe to? Well, I guess here is where we will just introduce a little bit of a concept. It's very fast. If we have two sources here, say they're R12, sometime t, okay? And we have our expanding universe, which we here take that we do have. We don't discuss that in any detail in this course, okay? And then, of course, the distance between these points, 1 and 2, and this will be then at the different point, 1 and the point 2 at a different point. Then their distance here will be R12 at some t0, okay? So then we can relate these R12 T with this scale factor R that we actually already tentatively introduced before. So you can see directly that it is defined such that if T0 is today, then R is indeed 1. And again, I remind you that this is often in the literature called little a. Yeah, when you compare this to what we do in galaxies later, in cosmology, so forth. Okay, but then if we take just the time derivative of this one, this is the R12 of t dt. So that will be r dot. That's just my shorthand now to write the r dt, right? But this is just a constant, so this is just t0. But of course, I can replace this now by the original relation. So this would just be then r dot divided by r, and then R12 of t. And that would be then v of t. So if we look at this, we can see that it has a certain form. We can write it in terms of v equal h times the distance between the two objects here, which I called r, where h is r dot divided by r, and that is called the generalized Hubble parameter. If you put now r equals to 1, yeah, so present day value, then h would be h0, that is for t equals to today. That would then, of course, be the Hubble constant. But in general, this is also a function of the redshift c. In that sense, you can see this as sort of a normalization parameters, perhaps. So, and then you can say, okay, but now, if these 2 points, which perhaps are 2 spiral galaxies like the Milky Way in the universe, are moving away from each other with a speed that is higher than the speed of light, which is allowed here because it's the expansion of the universe itself that causes this. So higher speeds than the speed of light are allowed. Then, of course, if they're emitting light toward each other, these light beams will never meet because they're receding with a speed that is faster than the speed of light. Okay? So by setting this to c, then, you can define a so-called horizon distance. So the horizon distance would be c divided by h of c. And this horizon distance, then, is a good measure for what we want to compare our photon mean-free path with. The question is, how do we get an estimate for this horizon distance? Well, since this involves now the Hubble parameter, which is the r dot, it's the time derivative of the scale factor divided by the scale factor, it's a function of c, there we do need a cosmological model, which I will not present here. You can look a little bit in the lecture notes. You can also wait for the spring where we will do this. But for a certain okay cosmological model, we have this expression that is 1.2 times 10 to the minus 18, 1 plus c, 3 1/2 per second. So I put it now in per seconds instead of the usual very nice units of h0. All right, so then of course we can just plug this in. So I'm going to take that at the time around the recombination, which we know happened at around 1000, but for some reason I did my estimate with 1100. Don't ask me why. Probably I had that in my head that, yeah, it's about 1100. So okay. Then this is 6.6 times 10 to the 23 centimeters as not a Hubble, but the horizon distance, of course. Okay? Using that in this. And this is then C divided by H of C. All right, so then we have a horizon distance of the universe. A characteristic size of our observable universe, if you will. Let's compare that to the mean free path. What did we have for the mean free path? Well, the mean free path was 1.9 times 10 to the 21 centimeters divided by x of c. So you can see directly that, okay, if we have fully ionized conditions, then x is around 1, then you can just look at this number and you can realize directly that the mean free path of the photon is much, much smaller than the horizon distance of the universe. And this means that as long as hydrogen was ionized, the photons were locally trapped in the universe, scattering around, not visible to us, okay? They were not set free. On the other hand, if we say the universe has become almost neutral, so the ionization fraction is 10 to the minus 3. In the same epoch, you know, it happened fast, remember that. Then we see that the mean free path suddenly will go from being much lower than the horizon distance to a great deal above. So, by just this super simple argument then, we can understand why photons indeed were set free during this epoch, which is often then referred to the name of photon-baryon decoupling, because the photons were decoupled from the baryons, meaning in this sense that, well, we didn't have any free electrons to scatter around, so there wasn't anything binding them together. All right. Now let's take that. We have worked with our mean free path argument. And now let's finally then work with our argument. I remind you again, we have had many times in the course some external observer viewing some object from above, and then we know that we see down is different. If this is a very optically thick object, so this here is much, much greater than unity, the optical depth, then we know that we see roughly 2 optical depth of unity. Okay. Now we do the same thing for the universe and our cosmological observer, which views this foggy cloud of last scattering. And when does this occur? Well, we know that it's going to occur around optical depth of unity. Where is this optical depth of unity now? Well, we calculate. We have kappa electron rho dl, okay? So first we use the same thing as before. So this is 0.5 x of c, ionization fraction of hydrogen, density rho 0, 1 plus c cubed, and then we're going to convert this path integral to a time integral, because ultimately we want to do it over redshift, right? We have this over redshift. So that's just dl dt, but dl dt in this case is just the speed of light c. Of course, we're dealing with photons after all. So we have 0.5, 4, rho 0. We have c. We have the integral from some t start to t today. We start early in the universe here, integrate in this direction now. X of c, 1 plus c cubed dt. So the only thing we have to do is to convert this time integral now. Okay? So of course we can use, we have that the r dt is our r dot, right? Yes. And what did we have more? Right. And we had that our r dot divided by r equals to our h, which is now a function of c. Okay? So by just then taking this, we can see that our dt is dr divided by r dot. We just replace it by this, such that it is then dr divided by r h, which is now a function of c. But now we want this, of course, in c space, so we want to do another one. We remember we had this the last time. This is the relation between the scale factor and the redshift c. It's just a straight relation like that, such that dc dr is minus 1 over r squared, which means that dt ultimately expressed in the redshift c, which we can integrate then, is going to be minus dc. We have r squared coming up there. We have 1 there, so the z r, but I don't want r. I actually want c, so 1 plus c h. You can check my algebra while I'm erasing this part. Okay. Now, let's plug this in to our optical depth integral, which is that one. So we're going to have that at 0.4. We're going to have a rho 0. We're going to have a c. And then we're going to replace it. So we're going to change the order of the integral so that it goes from t equals today, or whatever we want to do, t0, to some starting time. Yeah. And we're going to have x of c, and then instead of the t, we're going to have the c divided by 1 plus c of h, and then we have 2 there, so we're going to have this squared dc, but then I have my h of c in the denominator, and that's the general expression, of course. But then we actually applied, and now, of course, I took it away from the blackboard. What did we have? Yes, we assumed a cosmological model where this was to the minus 18, 1 plus c, 3, 1/2, you know. I'll leave it to you to evaluate if this is an Einstein de Sitter universe or whether it's an open matter-dominated universe where omega matter is 0.3. You can figure that out for yourself. Anyways, if we plug this in, we get tau approximately then 0.4 rho 0 c divided by this guy here, and then we have 3 1/2 and then this. So I will just plug out the numerical value, which comes out to be this one, 0.0354 it says there. And then it's from some t0 generally, I'm going to cite it, to some t equals to t start. So t0, this is actually an outside-in integral now. So we start from R and go inside, just like when we started from here and went inside. Remember, we could flip the axis up there and then go up here. And here we had the dt minus in the integral, which caused this to happen. We had x of c and then 1 plus c 1/2. DC. All right, so if you now solve for the psi equation like we did, you had a second order equation for the psi equation, and then you could solve for this. And then you can just integrate this, and that's a very simple numerical integration. A simple trapezoid rule will suffice. When you do this, you should, if you do it, reproduce something like the curve that is on the cover of the lecture notes. So that is a simple exercise for you that you can do now. We can, however, do also some simple analytic analysis of this. Let's say that we are in a small, to get the plausibility why this happened. Because if you do that, the full numerical integration, you will get something like this, where tau versus c, and then you will indeed see that you hit tau equals to unity at around c between 1100 to 1300, depending a little bit on your cosmological model and on various other assumptions. So that indeed the universe went from being optically thin, very thin, at lower redshifts, to optically thick at higher redshift. It happened fast, and it happened during this era of recombination. And now, because of what we have done, we know exactly why it happened. We can do a little bit of a plausibility analysis here by considering, instead of just taking it all the way from today to somewhere in the past, we can just consider a little region here during which we taggily say, okay, the ionization is constant during our little region. Yeah? Then we can consider a delta tau here, which then will be 0.00354, right? And then if this is roughly constant, we take it out, saying that this is our x of whatever C naught that we want to do. But we're going to do this on the era where C naught is much, much greater than unity, right? Yeah? That's around 1,000 or 1,500, we can say. Then it's almost fully ionized, so then it's going to be around unity, which means that this is not such a bad assumption for the era prior to recombination. It's going to be unity. Yeah? So you can take it outside the integral in that era. And this is a good, and then this integral we actually know by heart, so that's also very nice. So it's 2/3 C 3/1/2 C naught in this case. So if we now say that, okay, prior to recombination, this was 1, right? And we can say, let's take this to be 1,500. Then we see that delta tau during a short time period there, in that era, will be around this times 2/3. But then we have this, which is on the order of 1,500 times 3, and I think this will come out to around 100. You can plug it in and verify yourself. The point is that it's much, much greater than unity. So again, this is why the photons in the era prior to the era of recombination, they were locally trapped in the universe, not escaping, because the optical depth was so high, they could not freely stream. Then they were released during this era of photon-baryon decoupling, as we call it. And that's the era of recombination, and it has to and it's happened during this surface of last scattering, which is not really surface, but more of a cloud, as we said, a foggy cloud. Okay? And this is the exact reason. And this is also then the exact reason, if you turn around the argument, I started Wednesday by saying that, look, we know that from the course, we can never, for example, when we look at stars, right? We look inside, we can never see the interior of the stars because they're so optically thick. In the same way as if I put, we have talked about foggy days and clouds, right? If I put a lot of fog here, I can't see behind. And because the sun is so optically thick, we can never see the interior, right? But of course, we're at Leuven, so we know we put a caveat around that because we can do astroseismology, and we can then look at the star quakes here and perhaps get the information on the interior of the stars, but that's a different topic for another day, right? Now, by analogy for us here today, though, we can never see beyond this era of recombination. That's forever hidden to us, the information there. Can never have direct access. So no matter how powerful telescopes we build, no matter if we build JWST, JWST version 2, version 5, version 10, we're not going to be able to get beyond this fundamental barrier. Because then the universe was so optically thick, is veiled. We don't see it. And that's the essence of the analogy between this and that, and also, of course, why I call this a calculation of the photosphere of the universe. All right, that was it. We take a break until 45.